Linear independence. So here's a question. This is a set of vectors from R2, and I want to know if this set is linearly independent. And the answer is yes. And instead of defining linear independence, I'm going to give you another example. Is the set 1, 0, 0, 1, and 2, 3 linearly independent? So there's another set, again from R2, and the answer here is no, it is not independent. It is dependent. Linearly dependent, that is. And there's a pretty obvious difference between these two sets. This set, the first set, doesn't have any extraneous information in it. This one does, because I could get this vector by using a linear combination of these two vectors. So a set is dependent if you can write any one of the entries as a linear combination of the others. So I could write 2, 3 is equal to 2 times the vector 1, 0 plus 3 times the vector 0, 1. So this set is linearly dependent because in some sense one of the vectors depends on the other two. And so this is what you might call extra information. So this set is not as efficient as it could be. It has more vectors in it than it needs to contain all of the information that it contains. So adding this didn't add any information to this set. Now, that definition that I just gave you, that one of the vectors is a linear combination of the others, is not always easy to see, depending on the vectors, how big the set is, and so on. So is this set linearly independent? And the answer is, at least at a glance, the answer is, I do not know. And so what I would like to do is discover whether I can do this type of thing with this set. Can I write this as a linear combination of these two guys? Can I write this one as a linear combination of these two guys? Can I write this one as a linear combination of those two guys? That's a ton of stuff to check. So to check for independence, you try to write the 0 vector as a linear combination of the elements in the set. If you can write the 0 vector as a linear combination of the elements in the set in a non-trivial way, that is to not, because obviously I can write the 0 vector, if I want to write the 0 vector 0, 0, 0 as a linear combination of these three things, so something times the first vector plus something else times the second vector plus another thing times the third vector. Obviously I can do that by writing A equals 0, B equals 0, C equals 0. I have 0 times the first vector, 0 times the second vector, 0 times the third vector. I'd be adding the 0 vector 3 times and I get the 0 vector. But if that's the only way you can do it, if you must do it in that trivial way, then the set is independent. If you can find a non-trivial way, so some way to write this linear combination where at least one of these coefficients is not 0, then your set is dependent. So let's solve it this way. So here you'd have A, 2A, 3A plus 0B, 2B plus negative C, 0C equals 0, 0, 0. So you'd have the vector A minus C, 2A plus B, and 3A plus 2B plus C equals 0, 0, 0. And so you'd have A minus C equals 0, 2A plus B equals 0, and 3A plus 2B plus C equals 0. And so you could put this into a matrix, so it gets back to the stuff from the beginning of the semester. 1, 0, negative 1, 0, 2, 1, 0, 0, 3, 2, 1, 0. And then I could row reduce here. and see if I get a unique solution, the solution A equals 0, B equals 0, C equals 0, or if I get a non-trivial solution. So I'm going to leave the first row alone. So you watch me row reduce again. This minus 2 times that is 0. This minus 2 times that is 1. This minus 2 times that is 2, 0. This minus 3 times that. 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 And so you see you have a copy of the rows here. So we have 1, 0, negative 1, 0. We have 0, 1, 2, 0. This minus 2 times that is going to annihilate that whole row. And so if you come over here, you get A minus C equals 0, and B plus 2C equals 0, and C is free. So C could be anything. So let's say, choose, just to be simple, choose C equals 1. Then you get C equals 1, B equals negative 2, and A equals 1. So theoretically, if I plug in A equals 1, B equals negative 2, C equals 1 here, let me do that. 1 times 1, 2, 3, plus, minus 2 times 0, 1, 2, plus negative 1, 0, 1. And see what we get. We'd get 1, 2, 3, plus 0, negative 2, negative 4, plus negative 1, 0, 1 would be 1, plus 0 minus 1 is 0, 2 minus 2 is 0, plus 0 is 0, and 3 minus 4 is negative 1, plus 1 is 0. So I do have a non-trivial way to write the 0 vector as a linear combination of those three vectors. So this set is dependent. And you can see that if I could just bring this over, like I could write this minus this equals the negative of that. So if you can write the 0 vector as a linear combination of those three things, then you can write any one of those three things as a linear combination of the other two. So that is linear independence. You set it up, check to see whether you can write the 0 vector in a non-trivial sort of a way as a linear combination of the elements of the set. If you can, then it's dependent, the set is dependent. If you can't, then the set is independent. So let's look at a set of vectors from a different vector space. Let's look at the set 1, x, and x squared. These are vectors from the set of polynomials of degree 2 or less. Is this linearly independent? So let's check. The 0 vector in the vector space of polynomials of degree 2 or less is just equal to the number 0. So we'd have to write a times 1 plus b times x plus c times x squared. In order to make that 0 for all values of x, you'd have to have a equals 0, b equals 0, c equals 0. So a equals b equals c equals 0. So the set is independent. And that's a set of vectors from P2. Let's take another set of vectors from P2. Let's do, say, x plus 3 and x squared minus 2 and x. So is this independent or dependent? Well, we can find out by doing the same thing we did up here. So I'm going to take check for linear dependence. So you'd take a times x plus 3 plus b times x squared minus 2 plus c times x. We want to make that equal to 0, so I'm going to shuffle things around here. I have bx squared, and I have ax plus cx, so I have a plus c times x, and I have 3a minus 2b. That's equal to 0. So you have here, this will remind you maybe of, if you've had Calc 2, remind you of partial fractions a little bit. So I would need in order for this polynomial to equal this polynomial, because this is really 0x squared plus 0x plus 0. I would need for b to be equal to 0, because this coefficient has to be the same. I would need for a plus c to be equal to 0. And I would need for 3a minus 2b to be equal to 0, because the constants have to be the same and the x coefficients have to be the same. That's this equation. So we have b equals 0. which we can plug in here. That annihilates this term right here. So A is equal to 0, which annihilates this. So we get A equals B equals C equals 0. So the set is linearly independent. So that is linear independence, and of course we deal with different vector spaces also. So we have vector spaces that contain matrices, vector spaces that contain polynomials, we have vector spaces that contain points in n-dimensional space. And so you should be able to check any set of vectors from any of those vector spaces for linear independence. Okay, very good.